Hello class, we're on lesson number 3, chapter 8. We have two more properties of exponents, and we have here an illustration of children at a crossing, and you could just see this long line. Imagine that. Imagine waiting this out. Now, babies are currently born at a rate of about 130 million per year. Okay, that's a pretty big number, huh? A year contains approximately 530,000 minutes, which means that about 100, 130 million divided by 530,000 babies are born each minute. So doing the indicated division and rounding the result, we get 245. So we end up with 245 babies born each minute. Now, because the numbers in this calculation are very large, perhaps it would be easier in scientific notation. So let's just take a quick look here. Get my marker going. And what scientific notation allows us to do primarily is it allows us to use, oh, give me 1 second here. Okay, we got our pen back. Now, scientific notation allows us to simplify these types of problems where we have very large numbers, or in some cases very small numbers. And in this case, we'd have so many zeros. You'd have to be very careful that you just don't lose track of 1 0. Very easy to make a mistake. And even if you use a calculator, you'll notice that calculators will max out. And imagine if we just had a couple dozen more zeros on here, how would you actually be able to do this? Well, let's take a look at scientific notation. And what we would have done is we would have had we have the 130 million. Okay. And we're going to divide that by 530,000. Now with scientific notation, we could have written this as 1.3 times 10 to the 8th power, because we have here 8 decimal places, 1, 2, 3, 4, 5, 6, 7, 8. So we have 1.3. It's less than 10 and greater than 1, or 1 or greater. And then we divide that by, let me slide that over so at least be consistent here, 5.3 times 10 to the 5th power. Okay, so now the question is, well, how would we divide this? Well, given by dividing 1.3 by 5.3, we would have 0.245. Okay, so we'd have, this is going to be equal to 0.245. But now the question is, what about the rest of this? Well, what is 10 to the 8th power divided by 10 to the 5th power? Well, if we take a look here, we have 10 to the 8th. We have all of these 10s. We have 8 10s on the top, and we have 5 on the bottom. And we know that we could just simply cancel out all these 10s on the bottom as long as we're canceling on the top. We'd end up with 3 of them left over. 10 times 10 times 10, which is 10 to the 3rd power. So let's write that down over here. So we have 1.3 divided by 5.3, which is 0.245, times 10 to the 8th divided by 10 to the 5th, which is 10 to the 3rd. Now, it can be seen, okay, to divide 2 powers of 10, we simply subtract the exponents. Notice we have 10 to the 3rd. If we would have simply taken 10 to the 8th, okay, minus the 5th, okay. So here, I'm sorry, I shouldn't put parentheses around it, but I'm just trying to illustrate that what we have is 10 to the 8 minus 5th power, which is 10 to the 3rd power, okay. So we can see that we now have 0.245 times 10 to the 3rd power, and if we were to now write this as a number, well, we know that we can actually just move this decimal point, because this is times, it's a base of 10, so we move it over 1, 2, and 3, which means that this is 245. So that's the answer. Now, as you can see, let's just finish off what we had here. So 1.3 times 10 to the 8th divided by 5.3 times 10 to the 5th is going to be equal to 245. Just as the first law of exponents applies to the powers of numbers other than 10, this pattern of subtracting exponents is also true for division problems in other bases. And we can take a look here at the examples. As long as the base is the same, you have to be very careful, and we'll go over this in class, but you have to make sure that the base is always the same. So let's just go back here and take a look where we ended up with a very large number. We were able to remove all of these zeros, create a very simple decimal, 1.3 and 5.3. I think we could easily do this on paper just as easily as we can do it on a calculator. And then we're simply going to take this portion and do the math, which is 10 to the 8th minus 5th, okay? And that gives us 10 to the 3rd. So really very simple math is left over here. 1.3 divided by 5.3 and 8 minus 5. Very easy to get to this number if you know how to handle exponents and you remember how to how to do some simple division and some very simple subtraction. But let's just take a quick look here. We have example number 1. We want to show why 3 to the 7th, let's put that down, 3 to the 7th divided by 3 to the 2nd is equal to 3 to the 7 minus 2. Okay, which is also equal to then 3 to the 5th power, right? But we're not, they don't write it, but that's ultimately the answer there. But let's take a look. Why is it so? Well, if we were to just simply follow 3 to the 7th, we would have 3 times 3 times 3 times 3 times 3 times 3 times 3, right? That's 1, 2, 3, 4, 5, 6, 7. And we're going to divide that all by 3 times 3. Okay, so as we can see here, we have 7 threes, as they note. All right, so we have 7 threes as they write it down. And over here we have 2 threes. And we would simply subtract the 2 from the 7, which gives us 5 threes, right? And again, that would be the 3 to the 5th power that we had mentioned. This would be 7 minus 2. So, in essence, we have 3 to the 7 minus 2 power. Okay, and again, they're not writing it down ultimately. This really isn't simplified. You should be writing it in the end as 3 to the 5th power, okay, which is what we have here. Okay, we ended up with 5 threes. Okay, so I just kind of took it. They're just showing you this is very basic, how you're subtracting and why you can do it. If we look at the next one, it's to show why x to the 10th divided by x to the 6th is equal to 10 to the, or x to the 10 minus 6. And again, same illustration. We have 10x's, 6x's. You subtract 6 from the 10 and you end up with the 4. So what we have here is the rule illustrated by these examples is the second law of exponents. So the second law of exponents, let's clear up our board here real quickly. And the second law of exponents is a very important one because you're really going to be dealing with this extensively throughout the rest of your math life, understanding how to handle these exponents. It says here that if a and b and a minus b are positive integers, okay, and x is any number other than 0, then, and those are important things to know. You don't have to remember the key. It's just a habit of doing and understanding what they're saying. And there's reason why x is any number other than 0. I think we've gone over that simply in the very beginning of understanding exponents. x to the a divided by x to the b is going to be equal to x to the a minus b power. So when we have x to the a divided by x to the b, note that this is a form, and note that x would be the same. In other words, we have the same base. Let me tell you where this doesn't work. 7 to the fourth power divided by 5 to the third power. Okay? The base is not the same. There's a 7 and there's a 5. So we cannot simply subtract these exponents because we have a different base. Now, had this been 7 to the third power below, then yes, we could then say 7 to the 4 minus 3 power. So it's very important that you remember that what they're saying here is that x is the same base. Had it not been, they would have used another variable. For instance, y. Let's say x to the a divided by y to the b. And in that case, you again, was the sample that we have here, you would not be able to subtract them. You would just simply have that, you would have to do the math in itself. You'd have to do the multiplication and then the division. But when we have the same base, and we do have that base quite often in algebra, and particularly in the form of exponents. We're going to be, in the form of variables. We'll be dealing with variables throughout our math life, and we're just noting here that when you have these scenarios, you can simplify and you can express it as we have shown here. Now, in words, this law says that to divide powers of the same base, we subtract the exponents. In Lesson 4, we'll find out about negative exponents and see that this law holds for them as well. In our study of exponents, we have established two rules. One for multiplying two powers of the same base and the other for dividing them. Another useful rule helps us to find the power of a power. And here are examples on how it works. And we have the example 3. We have express 7 squared. I'm going to write it on this side. 7 squared raised to the third power as a power of 7. Well, by definition of the exponent, 7 squared to the raised to the third power would be 7 squared times 7 squared times 7 squared, right? Because we're taking 7 squared and we're multiplying it 3 times, right? So, but what could we do now? The first law of exponents means that we can actually add these up, all right? We can say 7 to the 2 plus 2 plus 2 power, which means that this is equal to 7 to the 6th power. Okay? But we also note that we can also, what we're basically doing when we're adding them is that we're really multiplying them. So this would have been the same as 7 to the 2 times 3 power. Okay? Okay, which give us the same, 7 to the 6. So we're either add them, or we can just say they're 3 times that number, which is 3 times 2, which is also 6. We can also use the next example. We have x to the 6th power, and it's being raised, I'm sorry, that 6 is too small, and it's being raised to the 4th power. So x to the 6th raised to the 4th power. How can we express this as a power of x? Again, we can multiply x to the 6th times x. Oops, that x is going to turn into almost a 4 there. We have x to the 6th times x to the 6th times x to the 6th times x to the 6th power. Okay, so that's 4 times. We can add them up and say 6 plus 6 plus 6 plus 6, which is 24, or we can express it as x to the 6 times 4, right, because there are 4 of them, and that would give us x to the 24th power, which is the answer. So these examples suggest the following rule. The third law of exponents, and that if a and b are positive integers, then, and let's write it over here, x to the a raised to the b is equal to x to the ab, or a times b. Okay, we know we can put two variables together. It means they're multiplied. So x to the ab power, x to the a raised to the b is equal to x to the a times b, or ab power. Okay, so that concludes lesson number 3.